Ladies and gentlemen, now, we will start our fourth lecture of the analyze phase. During the lecture, the following topics will be covered: transforming data, hypothesis tests. The goal from transforming data is to transform data of any distribution into data normal distribution. A number of statistical methods assume normally distributed data. If this assumption is not met, the generated statistical results are less reliable. If the data is inherently non-normal or skewed, calculations such as sigma level, PP, CP, PPK, and CPK assume normality and will therefore be affected. The benefits from transforming data are: data is transformed to make it better organized. Transformed data may be easier for both humans and computers to use. Properly formatted and validated data improves data quality and protects applications from potential landmines, such as null values, unexpected duplicates, incorrect indexing, and incompatible formats. Data transformation facilitates compatibility between applications, systems, and types of data. Data used for multiple purposes may need to be transformed in different ways. Here are examples for non-100% normal functions. To transfer the data, we will use a nonlinear transform function to align the data to a normal distribution, as shown in the examples. The steps to do the transformation are: ensure that the data stems from one population. Identify the necessary transformation function. There are different methods for transforming data. Linear transformations of the form AX plus B. As a rule, these do not change the distribution of the data. Nonlinear transformations, which are frequently able to align the data to that of a normal distribution. The usual nonlinear transformation functions are logarithms, exponential, logit, reciprocal, square, square root, and box-Cox, which can include most of the above functions and will be described in details. The box-Cox transformation is supported automatically by numerous statistical programs like SigmaXL and Minitab. Here are the transformation parameter Greek letter lambda, which is estimated simultaneously with the other model parameters, for example the mean value. Depending on the estimated lambda, the box-Cox transformation can correspond to one of the usual transformation functions. For example, lambda is equal to 2 corresponds to x raised to the power of 2. Which transformation functions are to be used? If the physical relationship is known, we can select a transformation that can be easily interpreted. If, for example, the relationship arises multiplicatively, the data becomes additive through logarithms, natural logarithm log of x. In practice, however, we have to work on a trial and error basis because the relationship is usually unknown. Test the data for normal distribution to see if the transformation has fulfilled its purpose. How can we perform a box-Cox transformation in Excel using SigmaXL? Click SigmaXL, then Analyze, then Data Manipulation, then click Box-Cox Transformation. Or click SigmaXL, then Process Capability, then Non-Normal, then click Box-Cox Transformation. Ensure that the entire data table is selected. If not, check Use Entire Data Table. Click Next. Select Data Heading, then click Numeric Data Variable, Y. The selected variable must contain all positive values. Note that, while this tool is often successful to transform the data to normality, there may not be a suitable transformation to make the data normal. The output report indicates the Anderson-Darling p-value for the transformed data. You may wish to check do not store if transformed data is not normal. Another option is do not store transformed data if lambda is equal to 1, falls within 95% CI. This latter option prevents you from using transformations that do not result in a statistically significant improvement towards normality. Before making transforming data, we should check the data for normality. To create a normal probability plot for the data, click Sigma XL, then Graphical Tools, then click Normal Probability Plots. Ensure that Entire Data Table is selected. If not, check Use Entire Data Table. Click Next. A normal probability plot of data is produced. If the data points follow the straight line fairly well, this will indicate that the data is normally distributed. Note that the data will not likely fall in a perfectly straight line. If the data points do not follow the straight line fairly well, this will indicate that the data is not normally distributed. Darling test from descriptive statistics will show p. If p is less than 0.05, this indicates non-normal data. The output of the Box-Cox power transformation are shown here. The most important outputs are optimal lambda and Anderson-Darling AD, normality test results, and the transformed data. As we mentioned before, p should be greater than 0.05 to pass the normality test. Also, you can check the Box-Cox power transformation curve. To do a normality test and create the normal probability plot for the data, using Minitab, click Stat, then Basic Statistics, then click Normal Test. The outcome will include the normal probability plot for the data and the mean value, standard deviation of the data. Also, they include the Anderson-Darling AD, normality test results. To perform the Box-Cox transformation in Minitab, click Stat, then Control Charts, then click Box-Cox transformation. The outcome of the transformation will include the lambda estimate and rounded value, the transformed data, in addition to Box-Cox plot. What is the Box-Cox power transformation? We want to understand the Box-Cox more deeply. The statisticians George Box and David Cox developed a procedure to identify an appropriate exponent, lambda equals L, to use to transform data into a normal shape. The lambda value indicates the power to which all data should be raised. In order to do this, the Box-Cox power transformation searches from lambda equal to -5 to lambda equal to +5 until the best value is found. The table shows some common Box-Cox transformations, where y is the transformation of the original data, y. Note that, for lambda equal to 0, the transformation is not y, because this would be 1 for every value, but instead, the logarithm of y. Now, we will see an example for the transforming data. We have a non-normally distributed cycle time data. Using the Box-Cox power transformation in a statistical analysis software program provides an output that indicates the best lambda values. The lower and upper confidence levels, CL, show that the best results for normality were reached with lambda values between -2.48 and -0.69. Although the best value is -1.54, The process works better if this value is rounded to a whole number. This will make it easier to transform the data back and forth. The best whole number values here are -1 and -2, the inverse function of y, and y to power -2, respectively. Histogram shows the transformed data using lambda is equal to -1, now more normally distributed. Now, we will introduce exercise for Box-Cox transformation of data. The table represents the collected data for a cycle time. We perform the normality test to see whether the data follows normal distribution or not. According to the histogram and normality probability plot, it is clear that the data is not normal and need to be transformed. Please do the necessary transformation using Box-Cox. Please pause the lecture and solve the exercise. The lower and upper of the confidence level show that the best results for normality were reached with lambda values between 0.423 and -0.573. Although the best value for lambda is -0.06. The transformed data have been shown in the table. Also, the Box-Cox power transformation plot with all the transformed data are shown. The Anderson-Darling p-value is shown and it is greater than 0.05, meaning that the transformed data is normal distributed. The histogram and normal probability plot show the transformed data now is more normally distributed. Also, the ADP value is 0.485, which is greater than 0.05, hence the data follows normal distribution. The table represents the collected data for a cycle time of a processing machine in minute. The quality engineer performed the normality test to see whether the data follows normal distribution or not. The data does not follow normal distribution, and from the histogram, it clearly shows data skewed one side. Please transform the data using Box-Cox transformation. Please perform the activity and send the output by email for assessment. Please download from the resources the instructional videos for transforming data using Sigma XL and Minitab, transforming data sigmaxl.mp4, transforming data minitab.mp4. The goals from doing hypothesis tests are: make it easier to decide on the validity of the assumptions made, for example concerning the parameters of a population. Verify the suspected causes. Ascertain statistical differences between two or more process outputs. Every statistical test involves the formulation of two complementary assertions, the null hypothesis and the alternative hypothesis. The null hypothesis, H0, describes the supposition that a test parameter equals a given value, or that the parameters of two or more populations are equal, the state in which nothing has changed. The alternative hypothesis, HA, on the other hand, describes the supposition that a tested parameter is unequal to a given value, or that the comparison of different parameters will show that at least one of these is different. The alternative hypothesis represents the change. Making decisions based on a statistical test entails a certain degree of uncertainty. One cannot be 100% certain that the decision is correct. There are two types of wrong decisions, or error types in statistical tests: the alpha error, or error of first type, and the beta error, or error of the second type. For a statistical test, both alpha and beta should be kept as small as possible. usually alpha equal to 0.05 and beta equal to 0.1. However, the smaller the alpha value, the larger beta becomes. The p-value, linked with the result of every statistical test, is calculated from the test statistic on the basis of existing data. If the calculated p-value is smaller than the alpha value, the null hypothesis can be rejected because the empirical error probability is smaller than what the tester has maximally allowed. Example, with alpha equal to 0.05, the null hypothesis is rejected when p is equal to 0.04. There remains residual risk of 4% that the null hypothesis is right after all. The following steps occur in a statistical test. Define the problem and goal, what is being investigated for which purpose. Formulate the hypothesis, H0, condition of equality. Set the significance level alpha, as a rule alpha equal to 0.05, or alpha equal to 0.01. Select a suitable statistical test, for example, two-sample t-test. Carry out the test statistic with the aid of a statistical software, for example, Sigma XL or Minitab. Interpret the test statistic, or p-value. Make your decision. Verify your decision. If H0 is not rejected, then verify beta. Let us check the 5 kinds of hypothesis tests for continuous data. There are 3 tests for testing mean values. First, one-sample t-test. Compare the mean value of a population with a target value. Null hypothesis, mu is equal to mu target. Alternative hypothesis, mu is not equal to mu target. N is greater than or equal 30, or normally distributed data. Second, two-sample t-test. Compare mean values of 2 independent populations. Null hypothesis, mu1 is equal to mu2. Alternative hypothesis, mu1 is not equal to mu2. N is greater than or equal 30, or normally distributed data, and independent samples. Third, two-sample, paired t-test. Compare mean values of 2 paired populations. Null hypothesis, mu1 is equal to mu2. Alternative hypothesis, mu1 is not equal to mu2. N is greater than or equal 30, or normally distributed data, paired dependent samples. There are 2 tests for testing variance. First, one-sample chi-squared test. Compare variance of one population with a target value. Null hypothesis, sigma2 is equal to sigma2 target. Alternative hypothesis, sigma2 is not equal to sigma2 target. Normally distribute data. Second, two-sample, F-test, or Levine's test, 2 variances. Compare the variances of 2 independent populations. Null hypothesis, sigma2 is equal to sigma2 Alternative hypothesis, sigma2 is not equal to sigma2 F-test, normally distributed data, while, for Levine's test, no distribution assumption, independent samples. How can we perform a hypothesis test in Excel using Sigma XL? Click Sigma XL, then Analyze Statistical Tools, then click one-sample t-test, or paired t-test, or two-sample t-test, or Levine for variance test. If necessary, please check Use Entire Data Table, click Next. How can we perform a hypothesis test using Minitab? Click Stat, then Basic Statistics, then you can click either one-sample T or two-sample T, or paired t-test depending on the type of test. Also, you can click one variance or two variances. Example for hypothesis tests. An engineer measured the Brunel hardness of 25 pieces of ductile iron that were subcritically annealed. The resulting data were as shown. The engineer hypothesized that the mean Brunel hardness of all such ductile iron pieces is greater than 170. Therefore, he was interested in testing the hypotheses. Null hypothesis, nu, is equal to 170. Alternative hypothesis, nu, is greater than 170. The engineer entered his data into Sigma Excel, and he requested that the one-sample t-test be conducted for the above hypotheses. He obtained the following output. The output tells us that the average of Brunel hardness of the N equals 25 pieces of ductile iron was 172.52 with a standard deviation of 10.41. The standard error of the mean SE mean, calculated by dividing the standard deviation 10.41 by the square root of N equals 25, is 2.082. The test statistic D is 1.2104, and the p-value is 0.119. Since the p-value, 0.119, is greater than alpha, which is equal to 0.05, the engineer fails to reject the null hypothesis. There is insufficient evidence, at the alpha equal to 0.05 level, to conclude that the mean Brunel hardness of all such ductile iron pieces is greater than 170. Let us do an exercise for hypothesis tests. The Acme company has developed new batteries. The engineer in charge claims that the new batteries will operate continuously for at least 7 minutes longer than the old batteries. To test the claim, the company selects a simple random sample of 100 new batteries and 100 old batteries. The old batteries run continuously for 190 minutes, with a standard deviation of 20 minutes, while the new batteries run for 200 minutes with a standard deviation of 40 minutes. The test claim that the new batteries run at least 7 minutes longer than the old one. Use a 0.05 level of significance. Assume that there are no outliers in either sample. Please pause the lecture and solve the exercise. The observed difference in sample means, 10, produced a t-statistic of 0.67. The p-value in this analysis is 0.2516. Since the p-value, 0.25, is greater than the significance level, 0.05, we cannot reject the null hypothesis. Thus, these results do not provide statistically significant evidence in support of the engineer's claim that the new battery will last at least 7 minutes longer than the old battery. Suppose we replicated this study many times with different samples. If the true difference in population means were actually 7, we would expect the observed difference in sample means to be 10, or less than 75% of our samples. And we would expect to find an observed difference to be more than 10 in 25% of our samples. Please perform the activity and send your output by email for assessment. Please download from the resources the instructional videos for hypothesis tests using Sigma Excel and Minitab. Hypothesis test sigmaexcel.mp4. Hypothesis test minitab.mp4. Thank you. and see you in the next lecture of the analyze phase.